In our previous session, we had seen about power available. Let us start off with rate of climb and time to climb in the session. Consider an aeroplane in steady unaccelerated climbing flight. The velocity along the flight path is v infinity and flight is inclined to the horizontal at angle theta. As always, lift and drag are perpendicular and parallel to v infinity, and the weight is perpendicular to the horizontal. Thrust T is assumed to be aligned with the flight path. Here, T is for climbing flight. It is also supporting a component of weight. Summing forces parallel to the flight path, we get T is equals to D plus W sine theta, and perpendicular to the flight path, we get L is equals to W cos theta. Representing the equation of motion for steady climbing flight, we get sine theta is equals to T minus D by W, where rate of climb is equal to V infinity sine theta. The right-hand side V infinity sine theta is the aeroplane's vertical velocity. This vertical velocity is called rate of climb, which can be represented as V infinity T minus D by W, since sine theta is equals to T minus D by W. Rate of climb increases with higher V infinity with higher thrust and lower weight. On the left-hand side, we have dV infinity as the power available and is represented by the PE curve. The second term on the left-hand side is dV infinity, which is level flight is the power required, as represented by the PR curve. For climbing flight, however, dV infinity is no longer precisely the power required because power must be available to overcome the component of weight as well as drag. Nevertheless, for small angle of climb, say theta is less than 20 degrees, it is reasonable to neglect this fact. The excess power is the difference between the power available and the power required. Hence, we can write rate of climb is equals to excess power by weight. PR curves as those already calculated for level flight, hence is an approximation to the rate of climb, good only for small theta. To be more specific, a plot of dV infinity versus V infinity for climbing flight is different from the plot of dV infinity versus V infinity for level flight, because V is smaller for climbing than for level flight at the same V infinity. To see this more clearly, consider an aeroplane with weight 2,275 kg with a wing area of 30 meters squared and parasitic drag coefficient of 0.015, Oswald efficiency of 0.6 and aspect ratio of 6. If the velocity is V infinity is equals to 150 meters per second at sea level, and if aeroplane is in level flight, then the drag coefficient is equals to 0.0175. Now, consider the same aeroplane in 30-degree climb at sea level. With the same velocity, V infinity is equals to 500 feet per second, we get the drag coefficient of drag as 0.0169. This should be compared with the higher value of 0.0175 obtained earlier for the level flight. As seen in this example, for steady climbing flight, L, hence coefficient of lift, is smaller, and thus induced drag is smaller. Consequently, total drag for climbing flight is smaller than that for a level flight at the same velocity. Now we can note that in this graph, the excess power is different at different values of V infinity. Indeed, for both the propeller and jet-powered aircraft, there is some V infinity at which the excess power is maximum. At this point, the maximum rate of climb is equals to maximum excess power divided by the weight of the aircraft. Now moving on to time to climb. To carry out its defensive role adequately, a fighter aeroplane must be able to climb from sea level to the altitude of advancing enemy aircraft in as short a time as possible. In another case, a commercial aircraft must be able to rapidly climb to high altitude to minimize the discomfort and risk of inclement weather or minimize air traffic problem. As a result, the time for an aeroplane to climb to a given altitude can become an important design consideration. The rate of climb was defined in a previous session as the vertical velocity of the aeroplane. Velocity is simply the time rate of change of distance. The distance here being the altitude h, hence rate of climb is equals to dh by dt. Therefore, dt is equals to dh by r by c. dt is small increment in time required to climb a small increment dh in altitude. The time to climb from one altitude h1 to another altitude h2 is obtained by integrating this. So t is equals to integration of h1 to h2 dh by r by c. Normally, rate to climb is considered from sea level, where h1 is equals to 0. Hence, the time to climb to any given altitude h2 is t is equals to integration 0 to h2 dh by r by c. To calculate t graphically, we have to plot r by c inverse versus h. The area under the curve from h is equals to 0 to h is equals to h2 is the time to climb from altitude h2. Graph here shows calculated and compared time required for CP1 and CJ1 to climb an altitude of 6096 meters. For the CP1 with the equation t is equals to integration 0 to h2 dh by r by c, the time to climb is equal to the shaded area under the curve shown. The resulting area gives time to climb as 27 minutes. For CJ1, which is plotted here, the resulting area gives the time to climb as 3.5 minutes. Note that the CJ1 climbs to 6096 meters in 1/8 of the time required for CP1. This is to be expected for high-performance executive jet transport in comparison to a propeller-driven piston engine counterpart. I hope you would have understood rate to climb and time to climb. Let us move on to range and endurance in our next session. Thank you.